Okay, study guide video 2. Now we're talking about graphs, position versus time graphs. Yay, we'll be done with these soon. So, the slope of a position versus time graph, remember that's your rise over your run of a graph, tells you velocity. Okay, so it tells you your change in position. So let's find one where we can look at that. These are like backwards. Your change in position, here, I'll just draw a quick one. Change in position over your change in time, so rise over run, is velocity. If you have a position versus time graph where you've got a straight line that's not a horizontal line, so that's like this line, okay, that's going to tell you that you're moving at a constant speed or a constant velocity because it has a constant rise over run. And like we just said, that gives you your velocity. So at every point along here, my rise over run value is the same. If an object moves backward for a position versus time graph, then I'm going to have a decreasing or a negative slope. Okay, so I'm going to have a slope that looks like this if I'm moving backwards because that means I'm going in a negative direction. A curve position versus time graph has a slope that's changing. So if I have a graph like this with a curve, okay, that's not a constant rise over run anymore. That means my velocity is changing, which means that I am accelerating, okay? Okay, so we're going to label these graphs down here with states of motion. This one has a flat position versus time, so this is going to be at rest. This means I'm not moving. I'm just standing in the same position as time goes along. Same with this one. I'm on a 0 position here. Here I'm at a negative position, but in all these cases, I'm not moving. Okay, I'm just staying at rest. I can be in different positions. The point is that for each of these, my position's not changing. I'm staying in the same position. These graphs are kind of backwards. I'm not sure. Oops, hang on a second. Give me 1 second. Okay. It thought I was asleep, I guess. These look like they're flip-flopped, but basically they should look like you should have one that looks like this. That's going to be a constant velocity in a positive direction. And then you should have one that looks like this, and that's also going to be constant velocity, but it's in a negative direction. Because this is going to give me a positive velocity value, which tells me I'm going in a positive direction because it's a positive slope. This is a negative slope, so it's going to give me a negative velocity value, which tells me I'm going in a negative direction. And then these two are both accelerating, okay? This one's speeding up, and then this one is slowing down. But they're both accelerating because they've got the curves, okay? All right, then we looked at position versus time, and then we looked at velocity versus time. So with velocity versus time, your rise over your run is your change in velocity over your change in time, and that gives you acceleration, okay? So if you have a straight line that is not horizontal, so a velocity versus time that looks like that, that means you're moving in a constant acceleration. That's your rise over run, is your acceleration value, and it's going to be the same. States of motion, if we're flat on a value, then we're in a constant velocity. This is a positive direction because it's above the x-axis. Here we're in another constant velocity, but we're in a negative direction because we're below. So with velocity, your sign tells you your direction. So if you've got a positive sign, if you're above the x-axis, you're going in a positive direction. If you've got a negative sign, you're below the x-axis, you're in a negative direction. If you're flat here on 0, then you're at rest because you're not moving. So your velocity is 0. Then all 4 of these different graphs where we've got a slope These are all some form of accelerating, and we really don't need to know like speeding up, slowing down, directions. I mean, you don't really need to go through those details for this. Just know that if you've got a velocity versus time graph where you have a slope, that means you're accelerating. That's what that rise over run tells us. And if we're above the x-axis, we're in a positive direction. So like this one and this one are in a positive direction. This one and this one are in a negative direction because they're below the x-axis. Okay. Okay, motion calculations. I think we can go through a few of these in this video. Here's some equations. Here's my velocity is my displacement over time, and then my acceleration is my change in velocity over time. So, okay, so we've got a warthog. I don't know what that is. He runs 15 meters in 4 seconds. What's his average speed? So we're going to use we can use our velocity equation for that. 15 meters in 4 seconds. Okay, and that's going to give me 15 divided by 4 gives me 3.75 meters per second. So I just divided his distance by his time there. Okay. How far can a cheetah run in 15 seconds if it's moving at this speed of 31 meters per second? We're going to use this same equation, but we're going to solve it for our displacement. So we're going to have V equals D over T. We want to solve for D. That means we're going to multiply both sides by T. So I get velocity times time equals displacement. So if I multiply 15 seconds times 31 meters per second, that's going to give me how many meters he ran. And that's 15 times 31 is 465. That's a lot of meters. Okay. What's the acceleration of a car that increases speed from 3 meters per second to 12 meters per second in 5 seconds? We're going to use this equation here. Okay. So we've got acceleration equals my final velocity of 12 minus my initial of 3 divided by 5. And that gives me 12 minus 3 divided by 5 is 1.8. And remember, acceleration is meters per second per second. So velocity is meters per second, distance or displacement over time. Acceleration is my change in velocity, which is meters per second, over my time. So sometimes you see meters per second squared. I always write meters per second because I like to remember that it's a change in velocity over time. Okay, what's the initial velocity of a car? Has an acceleration of 9. See here, they have meters per second squared. And comes to a stop in 7 seconds. So we're going to use this equation, but we're going to solve for final initial velocity. Okay, so we've got an acceleration of 9 meters per second equals final velocity of 0. Okay, so we're coming to a stop, minus our initial divided by 7 seconds is time. I got to shift things around and solve for this. So I'm going to multiply both sides by time. I'm going to get, I believe that's 63 if I remember my times tables. Yes. So 63 equals minus initial velocity. So my initial velocity is, let's see, this has got to be a minus acceleration here. If we're coming to a stop, it's going to be slowing down. So we end up with an initial velocity of 63 meters per second. So we were going 63 meters per second, and in 7 seconds, we came to a stop. So we could do 63 minus 0. That's like our change in velocity divided by 7 seconds. And that gets me back to my acceleration of 9 meters per second. But we're just using the same equation and solving for initial velocity instead of acceleration. Okay, free fall projectiles are next.